questions. Can you put in 13, 15, and 63 in the chat?
Looks like we got 13.
15, all right, and then put 63.
I think her mic is muted.
Sure, on the ice.
Should probably text her mic is muted. I think she's trying to say
That
something.
homework was kind of hard.
Oh, 13? I don't know.
Oh, yeah, she did. She's talking.
Dude, I forgot there was one
Dude,
more.
63?
63. I didn't attempt it, but I stopped doing the homework for the last 4 hours.
I forgot what we did.
Sorry? 6.6. Probably.
I have too much stuff.
Okay, good morning, everyone. I see already you put number 13 and 15. Do you have any more questions? Any more questions? Please put them on chat. Okay. Right, so we start with number 13.
I knew.
I didn't.
Hi, Professor Elias.
Hello, Rocco. Okay, you guys
Yeah,
have to be
you're
quiet or I will have to mute the class, so be careful.
It's set to.
Okay, so I start with number 13.
Mute us real quick.
Give us a sec.
Miss Elias, if you could hear us, we can't hear you. No, it's up.
Okay, yeah, there's just no audio for some reason.
Wait, type and ask Miss Elias if she could hear us. And ask her to type if she could hear us. Because we can't hear her.
Oh, they said we can hear
Oh,
you.
join us so we can.
Oh, okay, good.
So just mute us real quick, so we're not.
Okay, you guys can hear me very well. So I'm going to start. That's number 13. That's we have two curves. Y equal 2 to the x. So this one is y equal 2 to the power x. And the other one is the line y equal 3 minus x. And this is the region in between that we have to find its area. All right, so it's already sketched for us. So one less thing to do. So let us proceed. First, we need to find the interval we have to divide into pieces to cover this with little rectangle. To be able to do that, we need the intersection point. And they were very clear. They told us to find the intersection point by inspection. It means which value of x I should plug in this y and this y to have those equal to each other. So quickly, just by looking at them, which x will do it? What value of x? I plug it in y equal 2 to the x and 3 minus x, I get exactly the same y. Anybody can just look at it and tell me. So to find the intersection, we set the y's equal to each other. But this is hard to set. This is hard to solve. That's why they told us just do it by inspection. So as Jonah said, x equal to 1. Because if I plug in 1 here, I'll get 2. If I plug in 1 here, I'll get 2. So this is the intersection point. So I have my intersection point. Okay. And now we definitely have to know which is my upper curve. But in this problem, it's very clear. This is the upper curve, which is the line. Sorry, 3 minus x. And the lower curve is 2 to the x. So I'm gonna get rid of those to write it. So the way we do them, we take what we are calling the typical rectangle. So this is really the typical rectangle I'm gonna talk about. And here the upper is the same, the lower is the same. So I don't really have any issue with upper and lower because this is always the upper and this is always the lower. So I call this xi. So that's my typical rectangle. So this little bit here, this is my delta x. So area, the typical rectangle. The area is area of one of those rectangles. Is the length times the width. The width is this little bit, that's my delta x. The length of this rectangle, it means how much I have from here to here. If this is xi, it means this point here is 3 minus xi. This is right there. I take away from it 2 to the xi. And this would give me 3 minus xi, that's the length, minus 2 to the xi. That's the area of a typical rectangle. Now the area of the whole region is almost the sum. We're going to approximate it by the sum of those little rectangles. At this stage, I am thinking about covering it with those rectangles and adding them. That's the width of each one of them, and that's the length of each one of them. So that's the Riemann sum that approximate the rectangle. And finally, the area. Not the approximation. The area is what happened to those sum when n goes to infinity. And by the definition of definite integral, this is going to be equal to 3 minus x, that's my upper curve, minus 2 to the x, my lower curve, dx, representing this sum as an integral. The limit always, even though it's easy in this case, we always go back to the region, ask to cover this region with rectangle, which interval I need to divide. I need to divide the interval from 0 to 1, and these are my limit. Okay, so that's the setup. Now the integration, which is, I think that's what you had trouble with. Antiderivative of 3 is 3x, no issue. Antiderivative of x is a half x squared, no problem with that. Now the question is, so here on the side, I'm going to open a parenthesis and I'm going to emphasize what's the antiderivative of 2 to the x. That's the piece that we have difficulties. All right, anybody knows what's going to be the antiderivative of 2 to the x? Anybody have any idea before I proceed?
That was quite.
Let us remember from calculus 1. What's the derivative of 2 to the x? What's the derivative of 2 to the x? The derivative of 2 to the x, remember, it's not 2 to the x. It's the ln of 2 times 2 to the x. Okay, that's the derivative of 2 to the x. So if I want the antiderivative, we can do it 2 ways. One way is from here, that's one way, and I'll tell you another of doing it. From here, I say, okay, so if I take 1 over ln of 2 times 2 to the x, and I differentiate that, I should get exactly 2 to the x. So the antiderivative of 2 to the x, so that's one way to do it, is 1 over ln of 2 times 2 to the x. Okay, so it's not 2 to the x, this 1 over ln of 2. Okay, so that's one way by remembering the derivative of 2 to the x. Another way to do it is the following. 2 to the x is problematic. I'm going to take 2 to the x and rewrite it using the e. So the question is, how can I, because I know how to work with e, how can I rewrite 2 to the x using e? Okay, let me remind you of that. We did that in calculus 1, but let us repeat. 2 to the x, I can write it as follows. The 2 is e to the ln of 2 raised to the power x. True or false? 2 is e to the ln of 2. That's what e is. So this is going to give me e to the x ln of 2. So 2 to the x, I can write it as e to the x times the ln of 2. Okay, now what's the antiderivative of that? I can make a u substitution, u to be x ln of 2. The du is ln of 2 dx. And this would become the following. Integral of e to the u du, and the dx is 1 over the ln of 2. So we're going to get exactly the same thing, but this is actually the proof. How do we get there? So this would give me the following. 1 over ln of 2 e to the u. It means 1 over ln of 2 e to the x ln of 2. Now, I'm not really worrying much about the constant because I know at the end I have a definite integral. So finally, this will give me the following. 1 over ln of 2 e to the x times ln of 2 is 2 to the x. I close my parentheses. Okay, so two ways to find the antiderivative to the x. Either we remember that the derivative of 2 to the x is ln of 2 times 2 to the x. By dividing by ln of 2, I can recapture the antiderivative of 2 to the x. Or we can take 2 to the x, rewrite it as e to the x times ln of 2 and use a u substitution. Now we are ready to find the antiderivative. Please ask questions as I move on. Don't let go. All right, so now I go back and evaluate the area. So my area is right here. So the area is, now I find into every terms, so that's 0 and 1. Antiderivative of 3, easy, 3x. Antiderivative of that is a half x squared. Antiderivative of is 1 over ln of 2 times 2 to the x. So finally, the area is the upper minus the lower. It means 3 minus a half minus 1 over ln of 2, 2 to the x is times 2. Minus at 0, I'll have 0, minus 0, minus 1 over ln of 2, 2 to the power 0. So finally, I'll get the following. 3 minus a half, which is going to give me 5 halves, minus 2 over ln of 2, 0, 0, 2 to the power 0 is 1, minus minus, plus 1 over ln of 2. And finally, I will have 5 halves, minus 2 plus 1, minus 1 over ln of 2. And that's what give me the area. Okay, any questions before I move on? So the only difficulty was in this problem, I think, is finding the antiderivative of 2 to the x. So in general, the antiderivative of a to the x is 1 over ln of a times a to the x plus c. So that's something that we should do. Okay, questions before I move on to your second problem? Now I move on to number 15. Number 15. So I draw the graph clearly here. And this this is what I have. I have the graph of sine x, or like this, that's the sine of x. And then I have the graph of cosine. And it goes, so they have it in red, so I will do it in red. So cosine, we know that it starts here. And this is the graph of cosine. And the region in question is the following region. And this here is, they don't have to tell us, but we should be able to know that this is 0 pi over 2. And they want me to find the area. All right, who wants to comment about this area? So whenever we have to find the area, we look at the graph and we see what's my upper curve, what's my lower curve, what's the intersection, before we start doing the work. So what is the lower curve in this problem? What is the lower curve?
Sine x.
How could it be sine x? Why is this the lower curve?
It's the lower curve for the first half of the problem.
You mean the lower or the upper? Be very careful.
The upper.
Upper, right. What's the lower? Don't be afraid. It's the x-axis. It means y equal to 0. That's really what your lower curve is. Now, what's the upper curve? Is it changing or not changing? Quickly. It's changing. It's changing right here. That's where it's changing. So on the side, we have to analyze the problem. But before I can analyze it, I need to figure out what this point is. So it means I need to figure out the intersection between the two graphs because I have to know where I need to split. So I need to show intersection point. To find the intersection, I need to set sine x equal to cosine x and solve for x. Okay, how would you solve for x in this quickly? Any ideas? Or can you just tell me which value of x? Tell me the sine equal to cosine.
Pi over 4.
That's pi over 4. So sine x equal cosine x. You can just look at it. I say it's pi over 4. Or if you want, you can say that, okay, it means sine x over cosine x equal to 1. It means tangent x equal to 1, x equal pi over 4. So this intersection is pi over 4, sine pi over 4, square root of 2 over 2, square root of 2 over 2. So this point right here is the pi over 4. Okay, so we have to split. So for x between 0 and pi over 4, the upper curve, so up to here, the upper curve is the sine. The lower curve is obviously 0. And between pi over 4 and pi over 2, the upper curve is the cosine function, and the lower curve is 0. So to find the area, of course, here the rectangles, we don't have the same formula for the rectangles, so the problem really is changing. So the area is going to be, we have to split. So it's the integral from 0 to pi over 4 of sine x minus 0 if you want. You don't have to write it, dx, plus the integral from pi over 4 to pi over 2 of the cosine x minus 0 dx. And now the rest is fairly simple. Now we just evaluate. Antiderivative of sine is minus the cosine, evaluated between 0 and pi over 4, plus antiderivative of cosine is the sine, evaluated between pi over 4 and pi over 2. So finally, this is equal to minus cosine pi over 4 is minus the square root of 2 over 2 minus Cosine 0 is 1. Now sine pi over 2 is 1 minus the square root of 2 over 2. So finally, this is equal to minus, minus. So this is minus. Oh, sorry, this is a minus 1 here. No, this is 1. No, this is minus 1 here. So I will have minus square root of 2 minus square root of 2. That would give me that. 1 plus 1 equal to 2. Okay. Any other question from the homework? I'm assuming you guys are doing the homework. That's an important assumption in this class, or you will not make it.
Could you
Any other questions before I move on?
Could you please do a 63, I believe the number is?
63? All right, so we're gonna set it up. 63. I will not do the whole thing. I'll set it up, and let's see how it works. Okay. So I have 3 things. So I have that curve, which is 9 minus x squared. And I have 2 lines, so I will draw them in different colors. The first line is y equal 8x. And I have another line, y equal 5 half x. Okay, and the region in question is the region in between. Okay. So the first question is, okay, so the first question is, all right, I need to find this region. I have a lot to find. First, I need to find, what do I need to find first?
The intersection points.
We have to find the intersection, because which interval I need to divide? I need to find the intersection. And then we start to really kind of, talk about this. So first, let me work with the intersection. So intersection. And we have 2 things to worry about. So intersection, first I'm going to do between y equal 9 minus x squared and y equal 8x. So I need this intersection, all right? So I set them equal to each other. Minus x squared. And then this is gonna give me x squared plus 8x minus 9 equal to 0. Okay, and now I have to factor out, unless I can't. And of course, this is going to give me, it's a 1 somehow. So it is minus 1. And the other one has to be 9. And this has to be plus 9. X squared minus x plus 9x, correct. So this would give me x equal to 1, x equal minus 9. Definitely x equal to 1 is the one I'm interested in. Minus 9 is outside my domain. So this would give me the value here. This is a 1. Now I check. If I plug in 1 in here, I get 8. If I plug in 1 in here, I get 8. It means my intersection point is correct. I always do that. Now I need to find the other intersection point before I can really analyze this situation. So now the intersection between the parabola and y equal 5 over 2x. Okay, again, we have to set up the equality between them. So I write 5 over 2x equal 9 minus x squared. So this would give me x squared plus 5 over 2x minus 9 equal to 0. All right, and I need to factor this out. So I multiply across by 2 just to make my life easier. Equal to 0. Okay, and then we need to factor this out. Of course, one of them has to have the 2x, one of them has to have an x, and then we have 18. So which would be, so it's 2 and 9. I'm just guessing, I'm not sure. And plus minus. No, this is not gonna do it. Can anybody factor this out quickly? So how can we factor this out? It's 2x minus 2 and, okay, so 2x minus 9 and x minus 4, x minus 2. Sorry. 2x plus 9, x minus 2. Thanks for the factorization. Give me 2x squared, and that's give me minus 4x plus 9x, 5x minus 18. Correct. So this would give me x equal to 2. So this point here is 2. And I double check. If I put 2 here, I get 5. If I put 2 here, I get 5. So this is correct. So now we have the intersection. And now I go back and analyze. So how would you guys analyze this area? Tell me what you'd do. What is the upper curve in this region? What is the lower curve? And do I need to split? Do I need to split? Yes or no?
Yes, yes.
Absolutely. This is where things start to change. This is a 1. And this is right here is my 2. So now we have the situation between 0 and 1. Between 0 and 1, the upper curve is 8x. The lower curve is 5 over 2x. So that's the upper. And that's my lower curve. I draw my rectangle here. I see that a rectangle here and a typical rectangle here, I don't have the same formulas. Formulas are changing tremendously. So from here to here, the length is 8x minus 5 half-x. However, if I take this rectangle, the length is going to be 9 minus x squared minus 5 over 2x. So we know that things are definitely changing. And between 1 and 2, my upper is the 9 minus x squared, and my lower is the 5 over 2x. So it's only the upper which is changing. So now, finally, the area, I will not evaluate it. I will only set it up. We have to take 2 integrals, 0 to 1, 1 scenario, and 1 to 2. 0 to 1. The length is going to be, that's the length in this scenario, it's going to be 8x minus 5 over 2x. In the second scenario, so we have 2 different integrals. The length is going to be 9 minus x squared minus 5 over 2x. And the rest, this is a very simple integral. I will not do it. I will just set it up. Okay? Any other question before I proceed? Very good. So today we are going back to what I hinted at yesterday and finding area, find area. Using horizontal rectangle. Or sometimes we call it integration with respect to y. The way we've done it so far by taking the vertical rectangle, we call this integration with respect to x. Now integration with respect to y. Okay. All right. What I did yesterday, so you don't have to write this from yesterday. I talked about the horizontal length between 2 points. So if I have the number line, vertical line, and I have any 2 points on the line, I don't care where they are located, A and B, 0 could be in between, 0 could be here, then the length of this line segment, the length is always the right value minus the left value. So this is what we did yesterday. So I call this note number 1. Okay. Now another note we did yesterday was the following. And this time I'm going to ask you a question before I proceed to the idea. I'm going to give you the curve. I'm going to give you the following. Suppose I have this curve here. X equal y squared. It means I'm giving you x as a function of y. Okay. And here I have a line. Okay, so that line is, let's say y equal x minus 2. Okay, so this is question addressed to you. And I'm going to give you a value of y. This is a 1. I'll ask you the following question. I'm going to go from here, and I'm going to draw this line segment in red. Okay, I'm going to erase this. I'm going to take this line segment from this curve, which is, we're going to call it the left curve to the right curve, this line segment. This is 1. Who can give me the length of this line segment? I'll give you a minute to think about it. This is a 1 in here, and I'm taking the line segment that go from this curve, that we are going to call it the left curve, and to this curve. So who can give me the length from here to here? 1 minute. Okay, somebody gave me 2. Anybody else?
I think it's 2 as well.
Okay, who can explain to me verbatim, how did you get your 2?
You could just plug in the 1 as the x for both equations and then
Right.
solve it.
Exactly. This is my 1. So this is, you have the y. That's the y. So if this is 1, it means the x is 1. So I have this point. Done. Right here. I gave you the y. If you want to find this value, of course you have to solve for x here if you want. So you want the x value. So the x value is y plus 2. So if you know the y, which is 1, the x is going to be 1 plus 2. The x is going to be 3. So we have this point is 3. And this point here is 1, then the length is going to be 3 minus 1 is equal to 2. Is that very clear how we find the length? So let us say we a little bit kind of abstract this. So let us say I give you the same picture. I'm not going to change, the same curve. I will not change them. So this is xl equal y squared. And this is y equal x minus 2. And instead of calling this 1, I call this, let us say, y or yi. So when I say yi, it means in my head, from here to here, this is yi. That's really what I understand by it. And that's what I want you to understand. And now my question is, who can give me the length from here to here. What's the length of this segment? Quickly. Once we understand the picture, the rest is going to be fairly simple. What's the length of this line segment? Remember, yi in my head, it means, in this case, the yi is 1. So yi, it means from here to here. That's what the way I wanted to understand by yi. What's the length in terms of yi? What's the length in terms of yi? Do the same thing you did here with some abstraction. Anyone? Yi plus 2, exactly. We have the y. It means the x is yi square. It means this point right here is the yi square. I have that point. Now I want that point. I have the y. The x, I need to solve for it. The x is the y plus 2. So the length is going, so this point here is the yi plus 2, so the length is going to be the right value minus the left value. Okay, so whatever we're doing for x, we're doing it for y right now. All right, so now let us see what the general situation is, and then we go back to this example. So now let's see have the following setting. And by now you should almost see what I'm going to do. Let R be the following region. R is the region bounded from the left, bounded from the left by the graph of x equal g of y. So this time I'm giving you x as a function of y. From the right, by x equal f of y. And the lines y equal to c and y equal to d. So the picture in my mind is the following. That's the picture. So from the left, I have a curve. This is the left curve. From the right, I have another curve. So this is the right curve. XR for right, it's the f of y. And this is my left curve. From the left is g of y. The lines y equal to c. If this is c, y equal to c is this line. And this is a d, y equal to d is this line right here. And this is the curve I am interested in. Left, left, right, and the line y equal to c, y equal to d. And the question is find the area. We are going to proceed verbatim, the way we did previously. But instead of covering the region with those vertical rectangle, which is almost very hard in this case, because the upper curve, the lower curve are changing tremendously in this situation, we are going to cover the region by horizontal rectangle. But to be able to do that, it's the interval from C to D. So everything I did in the x-axis, now I'm going to change it. So I have to divide CD into pieces. So this time we're going to divide the interval CD into, and subintervals. Okay. And now there is no more delta x. And I'm gonna call delta y to be the length of every subinterval. So what's gonna play the role of delta x of each subinterval? So delta y. So right now I have from here to here, delta y is not delta x anymore. So these are my subintervals. And then, like I did previously in the previous problem, I will cover this region with rectangle. So I'm going to start here. I go from the left curve to the right curve. That's going to be the length. And these are the rectangles that I'm going to cover my region with. So from here all the way to here. These are the rectangle I'm going to cover my region with. So a typical rectangle. Focus on a typical one. It's going to go from the left curve all the way to the right curve. And this is the little bit. This is the delta y. That's my delta y. Another question. What's going to be the length of my, so a typical rectangle? The length, width, area. Now, what's going to be the length of my little rectangle here, from here to here? What's going to be the length? Like we did a minute ago. In this situation, I know the y is from here to here. To find the length, I need the x for this point, and I need the x here. Once I know these x's, I can take the difference between them. But we know that what you guys are given, if you know y, the formula is giving to the x. So this point here is going to be yi f of yi, which is the right value. So this here is f of yi. The same here. I know the y. And then this is the g of yi. So the point here is the g of yi. So the length is going to be the value of the right curve at the yi minus the value of the left curve at yi. So it's very crucial. It's the right minus the left, or we don't get a length. And that's verbatim what you guys gave me a minute ago. So this is f of yi minus g of yi. The width is the delta y. The area is length times width of every rectangle. Okay. So I'm repeating everything the same, but now y is becoming the variable, not x anymore. I'm not splitting the y-axis. Now finally, the area of the region is going to be approximated by the sum of those little areas. That's going to be the approximation, which is, again, we recognize in this a Riemann sum. A Riemann sum where the variable is y is not x anymore, but it looks exactly like a Riemann sum where the variable is y. So now what's going to be the actual area? It's going to be what happened to those sum when n is large. So by the definition of definite integral, it's going to be the following. F of y minus g of y times, and that's the important part, there is no more x's here. This is going to be dy. The variable is going to be dy. Now, the limit. Whenever we have limit, we go back to the region. Ask yourself, which interval you divide into pieces to cover the whole region with rectangle? The interval from C to D. So this is going to be the integral from C to D of that. So right now it's a problem where y is playing the role of x. I don't work with x in those problems. I work absolutely with y. And let us always remember that f of y is the right curve because I'm finding a length, and this is going to be the left curve. Right, immediately we have examples along those lines. Okay. So I would like to do two examples. Example number one is yesterday I took the following problem. I'm going to do it again. So let's see yesterday's problem. This is my region, the following. That's the region. So the region bounded by x equal y square and y equal x minus 2. That's the region. And the question is, find the area. So this is the region here. This is y equal x minus 2. And this is x equal y squared. And we need to find this area. Now, yesterday when we did this problem, we had an issue. Our issue was the lower curve changed. From here to here, I have one lower curve, and from here to here, I had a different lower curve. So when we did the x, when we did those vertical rectangle, we split. So today we're not going to do that. We're going to do it by taking horizontal slices. Now, if I take horizontal slices, what's going to be the left curve? What's going to be the right curve? If I take those slices, the line across the board is my right curve. It's not changing. That's my right curve. My left curve is x equal y squared across the board. It's not changing. It means regardless where I take my rectangle, I have the same left curve and the same right curve. So we are going to take those horizontal slices to do the problem. But now let us see how the process will go. First, I need the intersection point. Yesterday, I gave you the intersection point. Today, I'm going to tell you how to find it. There are two ways you can find intersection point. You pick the easiest. Either you set the y's equal to each other, or you can set the x equal to each other. So what do I mean by that? This is x equal y squared. I'm going to solve here for x in terms of y. And then instead of saying finding the x value that makes the y equal, I can find the y value that make the x equal, because solving those, setting this equal to that is easier than solving y equals plus or minus square root of x. So the intersection point, I'm going to set the x's equal. It means I set y squared equal y plus 2 instead of setting the y's equal. And now the rest is verbatim what I did yesterday, what we solved. I factor 2 and 1, y and y, and then minus and a plus. Y squared minus 2y plus y minus 2. And this gives me y equal minus 1, y equal to 2. So this time I set them equal, but I got the y, not the x. So I will have, this should be the minus 1. So down here is the minus 1. Those points are absolutely crucial for us. And this point here, up here, is the 2. Means this point here, the y coordinate is 2. And x is 4. I don't need it, but x is 4. And right here, the x is 1. So this is how we find the intersection point. So we have really flexibility for it. Either you set the y's or the x. Okay. All right, so now which interval I need to divide into pieces to cover it? I have to divide the interval from -1 to 2. Now, so first we will take horizontal slices. Part 2. When we take horizontal slices, we always have to express always x in terms of y. What do I mean by that? The first curve, I have x in terms of y. It's the second curve. Y equal x minus 2. It means x is y plus 2. So now this is my left curve, and this is my right curve. So I always have to express x in terms of y because I'm taking horizontal slices. Now a typical rectangle. Okay. So I'm going to call this, now to make life a bit easier for us, instead of call this yi, I'm going to call it y, just to make a little bit the writing easier. So when I say y, I want to remind you, it means this is y, from here to here. Be very careful. Y is not arbitrary for me. It's a physical quantity. It's from here to here. Now what's going to be the length of this rectangle? The length of this rectangle is the x value here of the right, that's the length, minus the right value, which is y squared. That's the length of this little piece. So, and the width is my little delta y. So a typical rectangle, the area of it is length times width. And for me, once we find typical rectangle, we're done. Minus y squared. Finally, the area of the whole thing is almost equal. Right now, I am thinking about covering it with little rectangle. So right now, I put the yi to remind me that now I am covering it. Right now, I am covering it. And finally, the area equal the integral. And now here you should be extremely careful. Extremely careful in the sense is that in this problem, y is the variable. I'm dividing the interval on the y-axis into pieces. Y is the variable. So this is going to be the following, the integral of y plus 2, the upper curve, minus y squared, the right curve minus the left curve. And what shall I put here? The x or dy? dy. Be extremely careful with those. Limit. Again, when I should limit, I go back to my picture. Which interval I split into pieces? I split that interval into pieces to cover the region. So it's going to be the interval on the y-axis from -1 to 2. I'm not looking at x anymore. So this is going to be the integral from -1 to 2 of y plus 2 minus y squared. The integration is very easy, so I don't feel I need to do the integration. Right? So that's how we integrate. So this is called integration with respect to y, because we look at y as my variable, and all my slices are this time those horizontal slices, because it's easier than taking the vertical slices. They avoid splitting in this situation. So now, whenever we have a problem, usually you look at it and you see which approach is easier to do the problem. Is it easier to cover with vertical slices? X is the variable. Or it's easier to cover with horizontal slices? Y is the variable. And sometimes either way will be absolutely work. So some of them are both ways the same. I mean, the amount of difficulty will be the same. Right? I guess I'm out of time. Okay, any questions before we move on? Before we end the lecture. Okay, so please do the homework for tomorrow. and ask questions. I'm going to assign number 63 again. I did it today for you. I'm going to assign it again. And the way I want you to do it the second time is by doing integration with respect to y. So I assigned it for today. We did it with respect to x. I'm going to assign it again for tomorrow, but I want you to do it integration with respect to y. It may think about covering it with those horizontal slices and see what you get. All right.
Bye, Professor Elias. Have a good rest of your day.
You too. Any other questions? Okay, bye-bye, guys. See you tomorrow.